Well, welcome to Chemistry 2045. My name is Emily Hyder, and I'm the instructor for this class. Let me tell you first what a definition for chemistry is so that we get set off on the right track. A good working definition is that chemistry is a science that tries to understand matter, how it behaves, what it does. The way we do that is we study the behavior of atoms and molecules, and it's worth our while to study chemistry because it touches so many other fields. For example, if you want to go into the pharmaceutical industry or become a medical doctor or study food and flavor science, you're going to need to understand chemistry very well. If you're interested in forensic science, if you want to solve the energy crises in the country, or if you're interested in the environment, understanding chemistry is going to be a really critical piece of that. So we're going to take some time to do it, but we haven't gotten very far down this path before we've run into some vocabulary problems. We haven't bothered to define some terms in our definition for chemistry, like matter or atoms and molecules. So our first order of business is to start to understand what some of these words mean. Now, most of you know what matter is already. Matter is just that anything that has mass and occupies space. So if this is our definition for chemistry is studying matter, we'll throw up a definition for what matter is. And matter's, of course, absolutely everywhere. Anything you interact with physically is composed of matter. Matter is found in the ice rings of Saturn. Ice is just two hydrogens stuck to an oxygen, chemically bound to an oxygen in the solid form. Right now we've already started going down the path of trying to figure out what molecules are. So these ice rings are composed of matter, and the matter is composed of water molecules in this case. Where else could you find matter? Matter is as close home as your teeth. If you look at your teeth, your tooth enamel, you've got matter there that we could study. The matter is composed of calcium ions and phosphate ions. So right away we're going to have to start defining what we mean when we're talking about calcium and phosphorus and try to define what atoms and molecules are. So here's some functional definitions for these. All matter is composed of atoms. What are atoms? They're submicroscopic particles. They're the fundamental building blocks of all matter. What do we mean by submicroscopic? An atom is about 10 to the minus 10 meters across. It's incredibly small. When we put two or more atoms together, we make a molecule. So a molecule is just two atoms stuck together. They could be the same type of atoms or different atoms, but when you've got two stuck together in something called a bond, a chemical bond, then you've got a molecule. So examples of molecules would be carbon monoxide, which is shown in this picture where carbon is represented by a black ball. There's an atom of carbon, chemically bound to an atom of oxygen. So this would be a molecule of carbon monoxide, and this is one of carbon dioxide. So we said that a molecule of carbon monoxide has a carbon and an oxygen. What we're talking about are two different elements. Elements are chemical substances that can't be broken down any further by a chemical change. They're pure substances. Right now there's about 109 of them that we know about. Of course, researchers are continually trying to make more, but right now our periodic table has about 109, and for example, one of those is aluminum. Everyone has encountered aluminum foil probably recently in their lives, and that's an example of a pure element. Now, if you stick two different elements together, for example, if you stick sodium and chlorine together like you see in this picture, you don't have a pure element anymore. What you have is a compound, a pure compound. So a compound is also a pure substance, and it's formed by chemically binding two or more elements together. So in this case, when you bind sodium and chlorine together, you get a new compound called NaCl, table salt. So element is a pure substance that can't be broken down any further by doing chemistry to it. You can break it down by doing physics or nuclear experiments with it, but chemically, a pure element can't be broken down any further. Now, elements can be polyatomic. So what do we mean by polyatomic? Think what you know about the word poly. Poly means many, and atomic means atoms. So elements can have many atoms chemically bound together. An example is pure sulfur. If we go down to the atomic level of sulfur, we see that sulfur has 8 identical atoms bound together, and it has this abbreviation S8. What it tells you is that when you see a subscript like this 8 is, it means that they're chemically bound together. 8 of these things chemically bound together. They're not just close to each other. There's a chemical bond there. So a subscript means chemically bound. So sulfur is an example of a polyatomic element. Chlorine is also polyatomic. Here's a picture of a chlorine gas, this yellowish gas. It has this abbreviation Cl2. So this tells you how many chlorines are bound together. Well, it tells you there's 2 bound together, and that's what's illustrated in this picture here. Now, gold is not polyatomic. Gold is monatomic. So when you have a chunk of gold like this, it means the atoms are close together, but not chemically bound together. So gold is monatomic, mono meaning one atom by itself, no chemical bonds. Chlorine is diatomic, di meaning 2 bound together, and sulfur is polyatomic. Now these are not the only elements that are polyatomic. Here's a list of diatomic elements. So if you got a sample of pure hydrogen gas, you'd have 2 atoms of hydrogen chemically bound together. Nitrogen's the same way, oxygen's the same way. Fluorine, chlorine, bromine, and iodine, these are all the same way. So these are the diatomic elements. Diatomic because there's always 2 bound together. Now if you are having trouble memorizing these or trying to remember what they are, I have a trick for you. There's mnemonics all throughout chemistry that will help you remember these things. And the trick I have for you to remember these diatomic elements that are abbreviated here in this list is to remember the phrase, have no fear of ice cold beer. And you'll remember hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. So when you see a picture of 2 elements chemically bound together like this is, you'll know it's one of these diatomic elements. So let's give ourselves a little test. We're going to give ourselves a test trying to identify whether or not we're good at finding out whether a chemical species is an element or a compound. And we're going to do it with this reaction here. This turns out to be kind of an important reaction. This was a reaction that was performed by a brilliant chemist named Antoine Lavoisier. And he did an experiment burning phosphorus in an oxygen environment to try to determine whether this phosphorus would gain mass or lose mass when it was burned. So he took an amount of phosphorus and he burned it in the presence of oxygen, and he weighed that phosphorus before and he weighed it after. And this was a really critical experiment because it disproved this alchemical theory called phlogiston, and he did it with an apparatus that looks like this. Now, we don't have such a fancy apparatus here, but I can show you a short video of what this experiment looks like. So, we'll watch. There's a little bit of phosphorus, that's the orange stuff, the reddish orange stuff. Let's put into our spoon. Lit with a lighter and just normal air. Air is about 21% oxygen, so there's a little bit of oxygen to get that burning going. And then they put it quite dramatically in that pure oxygen environment, pure oxygen in the glass. And you can see that chemical reaction going. Now, when he takes it out of the pure oxygen, you'll see a little bit of a white, cloudy substance left in the glass. Cloudy substance is our product, phosphorus bound to oxygen. So that's a pretty dramatic chemical reaction. Let's see what we can sort out from what we've got written down here. We start with pure phosphorus, we add oxygen to it, and we get this tetraphosphorus dicoxide in the end. Can you identify whether each of these things is an element or a compound? If it's an element, is it monatomic, diatomic, polyatomic? Think through it, and I'll show you the answer. The pure phosphorus, the elemental phosphorus, was an element. And the oxygen, what's that? That's an element. How about this tetraphosphorus decoxide? That's a compound. How about monatomic, diatomic, polyatomic? This is a polyatomic element. The oxygen, that's on our list of diatomics. And then of course, this is a molecule. So we've spent quite a lot of time trying to define things as elements or compounds, and you might wonder, why are we spending so much time on this? And it turns out that the chemical composition of matter determines its properties. And that turns out to be a really critical point. Let me demonstrate it by comparing two different chemical compounds. One is carbon monoxide and one is carbon dioxide. If we look at the properties of these two things, they're really radically different, even though at the chemical level, the atomic level, they don't look all that different. They're made of the same two elements, carbon and oxygen, but this one, carbon monoxide, is something that's quite poisonous. And the reason it's poisonous is because it binds to a protein in your blood called hemoglobin, and it displaces the oxygen from the hemoglobin, and it causes you to asphyxiate. You don't have enough oxygen. So this one's quite poisonous, but the carbon dioxide isn't. The carbon dioxide isn't poisonous because it doesn't bind to the hemoglobin. And the reason it does, it has 3 atoms chemically bound together. This one only has 2, so it looks a lot like diatomic oxygen. What other properties are different? Carbon monoxide burns with a blue flame, whereas carbon dioxide is incombustible. Carbon monoxide is colorless and odorless, just like carbon dioxide. So we've listed some properties here, and those properties are apparently literally a matter of life and death if you're exposed to one and not the other. But these properties also have other classifications we can assign to them. One of them is describing physical properties, and others are chemical properties. Chemical properties are the ones that describe how it reacts, what it binds to chemically, and physical properties aren't. So let's start talking about some physical and chemical properties. Physical properties are a way to classify matter, to identify it, and these are properties that can be measured or observed without changing the basic identity of it. So for example, if we want to describe bromine in this flask, you could say that some of it's in the liquid state, you could say some of it is in the gaseous state, and these would be physical properties. So other properties would be things like mass, color, odor, melting point, that's the temperature at which it melts, or the boiling point, the temperature at which it boils, density, solubility, these are all physical properties. So of course we must start defining the physical states quite carefully if we want to classify them as physical properties. And one of the striking things about physical states of matter, of course, you've had a lot of experience with solids, liquids, and gases in your life, but one of the striking things that is always interesting to me is that the only real difference between solids, liquids, and gases is the spacing between the atoms. For solids, the atoms are spaced very close together. For liquids, they are as well. But for gases, they're spaced quite far apart. Another real difference is that solids have very, very little kinetic energy. What we mean by that is they don't tend to move very much, but liquids do have a lot of motion, and gases, of course, do as well. They have the most kinetic energy. Gases are always in motion. So if we ask ourselves, what's the key difference between these 3 things? It's the spacing between the atoms and their kinetic energy. And that's what gives solids, liquids, and gases their properties. So solids, the particles are close together, they're fixed. And because they're close together, you can't compress them. You can't squeeze these molecules together anymore, so they're incompressible. And they also can't flow. They don't take the shape of a container. They're fixed in space. Now you can subclassify solids even more if you want to. When you look at a solid, like a chunk of diamond, as we like to do, this type of solid has a nice smooth face. It's optically transparent. It has sharp corners and smooth edges. And when a substance is like this, it's called a crystalline substance. And the reason it's crystalline is because the atoms at the atomic level are ordered in a nice repeating pattern. So when we have organized atoms like this, then the substance has that crystalline character. And examples of crystals that you've probably encountered in your life are things like crystalline salt or crystalline sugar. And those look like the crystals we're used to seeing on gemstones. Now you can make a crystal if you want to. You could dissolve something like salt or sugar in a little bit of water. In this case, I've dissolved a little bit of copper sulfate. And then as the water evaporates out, you can start to form the crystals. And you can tell it's crystalline because you see those nice smooth faces, smooth edges, and sharp corners. So if there's another type of matter that's not crystalline, what do we call that? And the thing that we call that, as I skip along, is amorphous. So an example of a solid that's amorphous is something like charcoal, and you can see it doesn't look crystalline at all. It's not smooth surfaces with sharp corners. It's not reflective at all. It's just a lump of charcoal. And the reason for this is because at the elemental atomic level, the atoms are disorganized. They don't have that nice atomic repeating pattern. So amorphous solids have randomly distributed atomic order, and examples of amorphous things would be like glass or plastic. Now you might be wondering, how can carbon, which is what charcoal is made of, be so different in diamond? And it really is, at the elemental level, these atoms are identical. Carbon atoms are the same in charcoal as they are in diamond. They're just organized differently. And because one looks better, we're willing to pay a lot more for one than the other. So let's keep going and write down what we know about liquids. Liquids have atoms close together, but they have kinetic energy. They're moving around, and that means that they do strange things like they flow. Now, because the atoms are close together, they're not compressible. You can't squeeze them closer together by applying pressure to them. That means it's incompressible. But they do take the shape of the container, and if you pour the liquid from this container into another one, its shape will change, but its volume would be constant. So how is that different from a gas? Well, a gas takes the shape of whatever container it's in, but it also occupies whatever volume is available. So liquids, the volume wouldn't change as you go from one flask to another, but with gases it would. If you uncorked this flask, the gas would flow out of it and then take the shape of whatever the bigger container was. So gas particles have a large separation between them, a lot of kinetic energy, and freedom to move. They're constantly flying around and bumping into each other. And that means that they are compressible. This is a picture showing a piston with the gas molecules inside it, and as you push down on that piston, they get closer and closer together. And at some point, if you do squeeze them close enough together, you'll go from the gas state to the liquid state. So a striking difference between the gases and the other two states of matter is that they're compressible. So we've said there are physical properties of matter that you can observe: size, mass, color, odor, melting point. Let's contrast that to chemical properties of matter. Chemical properties of matter describe the ability of that chemical substance to react with something else, to form a new substance. So chemical properties might be how flammable it is, how corrosive it is, whether it can be oxidized or reduced, or whether it's explosive. Of course, if you want to observe any of these things, you actually have to do a chemical reaction, and sometimes that can be quite hazardous. This picture is showing a oxidized metal surface rusting is a chemical reaction. So let's have a list of different processes and properties and see if we can identify at this point which ones are physical and which ones are chemical. So I've got a list of these properties. Quickly jot down which ones you think are physical properties and which you think are chemical properties. Now, hopefully, you've reached the same conclusions I have. So if we describe the color of something and the temperature at which it melts, we're describing physical properties. For this one, a metal dissolves in acid. That's describing a reaction and ability to react chemically, so that's a chemical property. Describing the metal density of something. This is its mass divided by its volume. That's a physical property. Oxygen reacts with a metal. We're talking about chemistry. And here it's describing how hard a metal is, a metal surface. That's a physical property. So if we have a look, B and C are the only two chemical reactions, and this is what those chemical reactions look like. So these are somewhat more striking and interesting for me to watch than just describing its density or its melting. So a physical change will occur when you take something from one state to another, a physical state to another. So melting ice, boiling water, subliming CO2. Subliming means going from the solid phase to the gas phase. That's what subliming means. So these are all physical changes. You haven't changed the chemistry of it when you do these changes. So let's look at this example really quickly. One of the really interesting misconceptions in chemistry is what happens when water boils. Isn't that funny? It's something we do all the time. But what does happen when water boils? If you ask a lot of students what happens when water boils, they think that you're taking water, which is H2O, as a liquid, and they think that these bubbles that form on the surface of the container as it boils, they think it's hydrogen gas, pure elemental hydrogen, and pure elemental oxygen. Now, that's a misconception because boiling is really just a physical change. What's in these bubbles is just water, but it's in the gaseous state. It's just separated in space. The hydrogens and oxygens are still chemically bound together. So we're just doing a physical change when we boil water. He said subliming is when you take a solid and change it to a vapor. So the solid is composed of CO2 molecules in this case that are stacked closely together, but they physically separate from each other in space. You can see the chemical bonds are still there. 2 oxygens bound to a carbon in the gas, 2 oxygens bound to a carbon in the solid. The chemical bonds are still there. The molecules are just separated from each other. So this subliming is also an example of a physical change. Now what about dissolving? If you take sugar, crystalline sugar, and you dissolve it in water, you're taking it from the solid crystalline state into what's called an aqueous state. Aqueous just means dissolved in water. So is that a chemical or a physical change? Well, let's look at what the chemical structure is in the physical solid state. The crystalline state shows nice ordered molecules. So here's one sugar molecule, here's another sugar molecule, here's another sugar molecule, and they're stacked close together in the solid state. But in the bottom picture, it shows the sugar molecule, the exact same sugar molecule, is just physically separated from the other sugar molecules. So the space is larger, it's surrounded by water, but not chemically bound to it. So when you dissolve something in water, like sugar, you aren't doing chemistry. That's just a physical change. So what would be chemical changes? Rusting, combustion, precipitation. These are all things where at the atomic level bonds are broken and formed. So let me sort of illustrate that. So if we had red diatomic molecules at the beginning near blue diatomic molecules, and these 2 blue atoms are chemically bound together, these 2 red atoms are chemically bound together. In the beginning of the reaction, they look like this, and in the end, the red and the blue are chemically bound together. So we've broken bonds between the 2 blues and between the 2 reds, and we've formed bonds between the blue and the red. So this is an example of a chemical change. Something new is formed, a chemical bond has been formed, so this is a chemical change. This is the same thing when you burn ethanol. If you had 2 carbon atoms bound together with 6 hydrogen atoms and an oxygen around it, if you burn it, you're adding oxygen to it, and in the end you get something entirely new. You get water and carbon dioxide. Incidentally, anytime you burn something, you add oxygen to it, and if you're burning something with carbon in it, you'll get water and CO2 out. So this is a chemical change because in the beginning the carbons were chemically bound together. In the end, the carbon is all bound to the oxygens. So we've broken chemical bonds and we've formed new chemical bonds. So burning propane would be the same thing. Here's a picture of a propane molecule before it's burned. In the end, you get that carbon dioxide and water out. Now, chemical changes often involve energy, change in temperature, either getting colder or getting hotter. I won't say always, but they often do. And it changes the composition of the substance. Rusting is a compositional change. An iron nail rusting would start with all the iron atoms, and then when the oxygen is added to it, the oxygens are chemically bound to the iron. So that's quite a different change. Rusting combines oxygen with iron and you get a new substance in the end. So we've got chemical properties, chemical changes, physical changes. How else can you describe matter? And one way is to describe its extensive and intensive properties. So let me tell you a definition for what we mean when we say extensive or intensive. An extensive property is something that depends on how much you have of it. So for example, mass is an extensive property. The mass of a substance depends on how much you have. The volume of a substance depends on how much you have. So these are examples of extensive properties. So if an extensive property is something depending on how much you have, what would the opposite of that be? Well, the opposite is an intensive property, and it's independent of the amount that you have. So intensive examples would be density, boiling point, specific heat capacity, electron potential. A lot of these things we'll define as we go. Density is interesting because it's an intensive property that's defined by 2 extensive properties, the mass and the volume. So if you take the mass of a substance and divide it by its volume, you get an intensive property out. And let me show you an example of an interesting case of density. If you compare the same volume of foam, wood, and lead, you have the same volume measured in cubic centimeters. The lead would weigh the most because it is the most dense. The wood would weigh very much less because it's not very dense, and of course the foam would weigh the least because it is not dense at all. So the foam would float on water, the wood would also float in water, but the lead would sink because the lead is more dense than water. The density of water is 1 gram per centimeter, so this is much, much greater than that. The wood is less than 1 gram per centimeter, so it would float. So this is quite an important intensive property. It has units of grams for mass per cubic centimeter for volume, or grams per milliliter. And what this tells you is an important relationship, that cubic centimeters and milliliters are the same thing. They're interchangeable units. And we said that the density of water is 1 gram per centimeter per cubic centimeter. And that is actually a very useful quantity to know. So let's say we wanted to tell the difference between a sample of mercury, a sample of platinum, and a sample of aluminum. How could we do it? Well, we could see that they're all metallic, they're all silvery, they're all shiny. So these physical properties aren't going to help us to determine which is which, how we can tell the difference, but what we could do is measure the density. We can also see that mercury is a liquid, so that would distinguish it from platinum and aluminum. But here's its density, 13.6, it's quite dense. Platinum is the most dense, 21.5 grams per cubic centimeter, very dense substance. And aluminum, surprisingly, is not dense at all, 2.7 grams per cubic centimeter. So you can separate which one is which based on its density, although of course they would all sink in water because they're all more dense than that 1 gram per cubic centimeter.